Hello, in this video I'm going to talk about electromagnetic induction, one of the most useful phenomena that's ever been discovered in the history of humanity. This lies at the heart of electricity generation and electricity distribution. So it makes it foundational to everything in modern society. And it has been for the last couple of hundred years. This is Michael Faraday discovered electromagnetic induction back in the early 19th century. And it wasn't long after that that people started producing electrical generators and completely revolutionized the world. So what do we mean by electromagnetic induction? Well, this is where we have relative motion between a conductor and a magnetic field. So it could be we move a wire through a magnetic field. We could rotate a magnetic field around a coil of wire, something like that. As long as we've got relative motion between the conductor and the magnetic field, and that relative motion will induce, i.e. bring into existence, an EMF in the conductor. And if that conductor is then joined up to be part of a circuit, then that EMF will drive an electrical current. So we're getting relative motion here. We've got a motion of a conductor in a magnetic field, and that motion is producing electricity. So you can see how this is the foundation of the electrical generator. It's also the foundation of transformers as well, which is central to distributing electricity. And I'll get onto that later on. So how are we going to describe all of this mathematically and quantify in some way what EMF we're actually inducing? Well, we need to extend our descriptions beyond the B field, beyond magnetic flux density, which we've been talking about up until now. And the first thing we need to now talk about is just magnetic flux, which we represent with a Greek letter phi. So magnetic flux density is, well, flux, first of all, when we're describing flux and we're using that word, we're talking about something which propagates through space or appears to propagate through space. So in terms of a magnetic field, we've got these magnetic field lines that we draw out, which, they're directed through space. And we've got this magnetic field, which is extending through space. So when we're talking about flux, we could describe these lines as being lines of magnetic flux. So when we're describing the strength of this field, which we're doing with our B here, with our magnetic flux density, we're saying, right, well, how much flux, which in pictorially we can say how many of these magnetic field lines, how much flux is going through unit area in space? If this magnetic field is extending through space, we can take some surface area in space and say, right, well, how much of our magnetic field is passing through that unit area? So our magnetic field strength, our magnetic flux density B, remember these two terms are more or less interchangeable, the magnetic field strength and the magnetic flux density. Well, our flux density is the flux per unit area. If we're looking at how it's propagating through space. So that makes it quite easy then to move from magnetic flux density B to magnetic flux phi, because we just need to multiply by the area, well, and also get the component of the field which is perpendicular to that area. So as I've drawn it here, everything might be going through the area perpendicularly, but of course that might not always be the case. It might be going through at some angle here, in which case if it's at an angle theta to the perpendicular, we need to get the perpendicular component of the B field that's going through this particular surface. So our magnetic flux is then going to be B multiplied by cos theta. That gets us our perpendicular component. Then we multiply by the area to go from flux density to flux. So that's how we work out what the magnetic flux is. Right, the units of this are Webers, which is represented by a WB, capital W, lowercase b. And we can see from this formula here that 1 Weber is equal to 1 Tesla meter squared, because we've got Teslas for the magnetic flux density, and then we've got meters squared for our area. Right, the reason that the magnetic flux is important is we then move on to a new term again called magnetic flux linkage. And this is where we start bringing the conductor into the equation, because we were saying at the beginning, this induced EMF, it depends upon the magnetic field, or more specifically the magnetic flux, but it also depends upon the conductor. So we're now making this linkage between the flux and the circuit. So say we've got, and here we're going, full on classical physics here. We're doing a full on empirical finding that Michael Faraday came up with back in the day, 200 years ago. Michael Faraday, one of the ultimate kings of empirical, and experimental physics. He conducted all of these experiments, and he found this connection, this relationship between magnetic flux linkage and the induced EMF. So he then saw that if we had some loop of coil, so say we've wound up multiple windings of a wire into, well, in this case, I'm doing a circular coil, but it could be any old shape. And we say, well, we've wound that wire up n times. So, if we had 10 loops of wire here, then our capital N will be equal to 10 in that particular case. It's just how many times have we wound round the wire. Then if we multiply that N by the magnetic flux through the coil, so here we're taking A, our area, to be the area inside the coil. How much area is this bit of circuitry actually taking up? Then our magnetic flux linkage is capital N multiplied by the magnetic flux phi. So that is our magnetic flux linkage. And then the big finding that Faraday had, so much so that is now called Faraday's law. And as I say, this is an experimental finding that he came up with. And this is all we can deal with at the moment, seeing as we're in classical physics. We're not going to be putting some lower level theoretical underpinning to this before we head off to university. This is a straight empirical finding that Faraday came up with, is that the induced EMF is proportional to the rate of change of magnetic flux linkage. So here we're putting in our deltas for our rate of change here. So our change in magnetic flux linkage divided by our change in time. This is our rate of change of magnetic flux linkage. So that's what Faraday discovered. And this is something that we can quantify. Now, and we don't even have to get into the details of calculus here. We don't have to turn these deltas into d's. We're not doing a dn phi by dt. We don't have to do that yet. Now, we could do, but there's a lot of examples, as I'll bring up in practice questions, where we can do this with capital deltas rather than turning it into more full-blown calculus. So we've got this, but of course we really want to turn this proportionality into an equation, which is where Lenz's law comes in. So Lenz, he came up with the constant of proportionality, which he set as being a -1. So we've now got the induced EMF is equal to minus the negative of the rate of change of flux linkage. And this is a conservation of energy issue, really. If you think of what's happening here, we are moving something through a magnetic field and we're getting transfer of energy from one place to another. So that motion must be doing work against something. If we're staying in the language of classical physics, there must be some force that we're doing work against. We're pushing against the B field in some way. So what is happening there? Well, when we induce the EMF in the conductor, then we're going to get a current flowing. If we've got this all hooked up to a circuit, and that current that we produce is then going to produce its own magnetic field going around the wire according to the right hand grip rule. So then we'll have two magnetic fields in play. We've got our external B field, and then we've got the magnetic field associated with the induced current. These two fields need to oppose each other. We know with magnetic fields that they all have north-south polarity. We don't get just monopoles. Everything has a north-south. So the magnetic field that we're creating must have a polarity which opposes the external magnetic field. This then means that we're going to be pushing norths together or pushing souths together. It means we're doing work against something, and by doing that work, that's how we're transferring energy into the electric current. So, for example, one that they quite often like is when you get the coil of wire and then you push a bar magnet into the coil of wire. So if we push the bar magnet in north end first, then the direction of the EMF and therefore the induced current and therefore the induced magnetic field will be in such a direction that we'll get a north at this end of the coil and a south at the other end. So that these two norths will be opposing each other, and we have to actually push the magnet in. We have to exert effort getting the magnet into the coil. If it created a south at this end, well, it would just suck the magnet in. We wouldn't have to do any work, and we'd be creating electrical current out of nothing. Similarly, when the magnet comes out the other end of the coil, we need to reverse the polarity here. The EMF will change direction, so we've now got north at the left-hand end, which means it will act to keep the south inside the coil. So this is what Lenz's law is describing, that the direction of the induced EMF will be such that it acts to oppose the action that's creating it. So if we're pushing the magnet in, and the EMF will set up to oppose that pushing in. So it will create a north here, which will repel the magnet. If we're taking the magnet out, it will oppose that action. It will create a north at this end in order to try and keep the magnet in. So that's what Lenz's law tells us, that the induced EMF acts to oppose the action that creates it. And that is a conservation of energy principle, so that we have to do work in order to create the electrical current. Right, so that's pretty much covers all of the basics of electromagnetic induction. We're going to be doing some practice questions based on the combination of Faraday's law and Lenz's law. We can actually quantify all of these things, and then we'll be looking at what sort of things can we change? How do we get a change in magnetic flux linkage? We can see that this is what it depends upon in order to induce an EMF. We have to change something in magnetic flux linkage. Well, we know that magnetic flux linkage is NBA cos theta, so we have to change one of these four things. Now, it's easiest to change the angle. Once we've set up a coil of wire, changing the number of loops in the coil is not something you really want to do in the middle of actually using it. So we tend to keep N fixed. Similarly with the magnetic field, you set up an external magnetic field, it's easier to leave it as it is rather than keep changing that. The same with the area of the coil. Again, it's not something that's that practical to change compared to other things. Whereas the angle between the coil and the external magnetic field, you can change that easily. You can spin the coil around, or you could spin the magnetic field around on the outside, change the direction of all the field lines. So it's this angle theta which is easiest to change. And as I say, that is the foundation of the electrical generator. If you spin a coil of wire inside a magnetic field, or you spin a magnetic field around a coil of wire, you've then got a change in magnetic flux linkage, and that's going to induce the EMF. And of course, the faster you spin it, the faster the change in flux linkage, which means the greater the EMF that you're actually going to induce. So this is the sort of thing that we're going to be investigating in practice questions, and we can start putting these equations here into action. Right, so I'll leave that there for now. In the next video, I'm going to go on to transformers to talk about how electromagnetic induction works there. We're pretty much totally dependent upon transformers in day-to-day life, so it's worth knowing something about how they work.